All right, here we are at Chapter 3 in our review of Semester 1. The topic here is proof, which I have said before is the central concept of the class. So what we'll do, not initially, but after a little bit of preparatory work, what we'll do is actually give the first proofs of the class. So we do have to do a little preparatory work. We first of all have to talk about a conditional statement. We will find that in every proof that we give, we will ultimately have proven a conditional statement, and that structure will be important to us, so let's talk about it. A conditional statement, by definition, is a statement of the form if blank, then blank, and you can fill those blanks in with any substatements that you like. So here's an example of a conditional statement. If two angles are vertical, then their sides form two lines, which, side note, we know expresses the definition of vertical angles. Now we have names for the statements that go into those two blanks. We call the statement that comes immediately after the if the given. We call the statement that comes immediately after the word then the conclusion. So then every conditional statement has the form if given, then conclusion. So we had this example, if two angles are vertical, then their sides form two lines. Given my definition of given and conclusion, we say then that the given is two angles are vertical, and we say that the conclusion is their sides form two lines. Now, very often we'll encounter statements that, though really conditional in form, don't have that explicitly present in the way that they've been stated. And a conditional like that is often called an implicit conditional. That is, it's a statement that can be re-expressed in a synonymous way, but a way that uses the if-then form. So, for instance, consider this, the statement supplementary angles sum to 180 degrees, which obviously doesn't contain an if or a then, but really this is a conditional statement. This is then an implicit conditional. And if we were to write this in conditional form, we would have what you see. If two angles are supplementary, then their sum is 180 degrees. And clearly that is synonymous with the original statement, but now we have made the if and the then explicit. This will be one of the steps that we often have to undertake when we give our proofs. That is to take a statement that isn't explicitly in conditional form, but we express it in conditional form. Here's a second example. The non-common sides of a linear pair form a line. What would this be in conditional form? You might take a moment to consider this and attempt to answer yourself. And here's the answer, very quickly. If two angles form a linear pair, then their non-common sides form a line. And I think clearly, once again, this is synonymous with the original statement. And now we have explicitly in front of us the if and the then. False conditionals. Occasionally we will encounter a false conditional, and we need to speak about this correctly. A conditional is false when we can provide a counterexample to the claim that it makes. That's how we show in this class that a claim is false. We provide a counterexample. And what is a counterexample? It is some object or objects, for us typically geometrical diagrams, that will make the given true and the conclusion false. Let me give you a simple example. Consider this conditional statement. If an integer is prime, then it is odd. Take a moment to understand what that means. If an integer is prime, then it is odd. Well, that clearly is false. And why is it false? It is false because it has a counterexample. And the counterexample is the number 2. That's the object in this case. And why is it a counterexample? Well, 2 is prime, but it is not odd. 2 is even, of course. So what 2 does is it makes the given true. The given is an integer is prime, and 2 is prime. But it also makes the conclusion false because 2 is not odd. Converse. We will very often talk about the converse of a conditional statement. This is language that occurs all throughout the class. The way that you get a converse of a conditional statement is you simply exchange the given and the conclusion. You flip them around so that each occupies the position that the other did occupy before. So for instance, here's a conditional statement. If two angles are adjacent, then they share a side. If we form the converse of that, we have then, if two angles share a side, then they are adjacent. And notice what we did. We simply exchanged the given and the conclusion. I have an important point that I simply must make about converses. It's a point that I will make again throughout the class. This is a common mistake that students make. Note that some true conditionals have true converses, and also, and this is perhaps more important, that some true conditionals have false converses. So I've got an example of each. I've got two conditional statements, the first of which has a true converse, the second of which has a false converse. So my first conditional is this: if an angle is right, then it measures 90 degrees, which of course is true, simply by definition of right. And if you flip this around, that is, if you form the converse, you get if an angle measures 90 degrees, then it is right, which is also true. So that's an example of a true conditional that has a true converse. But now let me give you an example of a true conditional that has a false converse. And it's this: if two angles form a linear pair, then they are adjacent. So let me simply draw you a very simple example of this. So let me draw you a linear pair. This is something that you're supposed to know how to do. So you simply make a line, and then out of that line you make two angles, which I will call angles 1 and 2. That's my linear pair, and those angles are certainly adjacent. They have a common side, and their interiors do not overlap, so they are certainly adjacent. But now consider the converse of that conditional statement. The converse would be, if two angles are adjacent, then they form a linear pair, which is clearly false because, well, consider this. Angles 3 and 4. They are clearly adjacent because they share a common side and their interiors do not overlap, but they are not a linear pair. So this is what happened. I took a true conditional statement, I formed its converse, and that was false. Now, the lesson that we have to learn from this is that we can never assume that simply because a conditional statement was true, that its converse must be true as well. Some true conditionals have false converses. So here's an example where this will arise. We'll prove in a later chapter, the chapter on congruence actually, that if a triangle has a pair of equal sides, then it also has a pair of equal angles. That's the conditional statement that we will prove true. Now the converse of this is, if a triangle has a pair of equal angles, then it has a pair of equal sides. Now that converse, we will have no right to assume that it's true even after we have proven the original conditional statement. If it's true, we'll have to prove that it's true, and if it's false, well, we'll give a counterexample. It turns out that it will be true as well, but that will demand its own proof, and that proof will not be identical to the proof of the original conditional statement. All right, now let's turn to the concept of proof, the central concept of this class. What we do in this class is we prove theorems. Almost all the work that we do will be of that form. Now, we've actually seen proofs before. I mentioned this, but didn't make too much of it. The inference chains that we gave in the previous chapter, those were actually proofs. That's what a proof looks like. And in each, what we proved is that the final statement does indeed follow from the given. That is, if we start with that given and apply various definitions and postulates, we can arrive at the final statement. And so we have proven that the final statement is true if the given is true as well. So let us call that final statement the conclusion. Thus, in each of those inference chains, we prove that if the given is true, the conclusion is true as well. So perhaps you can begin to understand the importance of conditionals here. What each of those inference chains actually proved was a conditional statement. We proved that if the given is true, then the conclusion is as well. Now, here's our definition of theorem, a word that went by very quickly in the previous chapter, but now we can define precisely. Once we've proven a statement of the form if given then conclusion, we call that statement a theorem. And what we do in this class is we prove theorems. We are theorem provers. That's what actually mathematics really is. It's the proof of theorems. Now, before we actually give any proofs, let's talk about how the proofs are set up. This is something that I need to describe in great care, and this is something that I will have you do on the worksheet as well. So here's how proofs are set up, and we'll do some examples, of course. Write the statement that you will prove in conditional form. If it isn't already, sometimes they are, sometimes they are not. Then, very important, we will draw and label a diagram to illustrate the given, not the conclusion, but just the given. And then we will write the word given, and after that, the given is the proof. After that, we will write the word prove, followed by the conclusion at which we are supposed to arrive. And we will make certain that this refers to the diagram that we have given. And in this way, our proofs will always be specific. Now, let me show you some examples of this. Now, I will not go and actually give the proof. That's a task for a little bit later. But simply, at first, I wish to set the proof up. So let us prove that linear pairs are supplementary. So let's first of all put it in conditional form, and you'll allow me to abbreviate a little bit, of course. If two angles form a linear pair, LNPR for linear pair, then they are supplementary, SUPP for supplementary. So there is the statement in conditional form. And now we draw a picture, step 2, we draw a picture to illustrate the given. We don't attempt to illustrate the conclusion yet because we don't actually know that the conclusion is true until we've given the proof, but we can illustrate the given for sure. So let us create a linear pair. Okay, we know how to create a linear pair, of course. You begin with a straight angle. There, look, straight angle. And we divide that into a pair of adjacent angles. And let's give these names. And I think I will use 3-letter names for each of my angles. So how about point names ABC and then D? And then, as I said, what we're supposed to do is to write the word given, followed by the given of the proof. And this refers specifically to the diagram as given. So angles ABC and CBD are a linear pair. Let me fix that. Are a linear pair. And what we wish to prove, and so there it is, the word prove. What we wish to prove is that angles ABC and CBD are supplementary. And notice how all of this is quite specific. I didn't say just generally we have a linear pair or vaguely that two angles are supplementary. Instead, in the given, I named the angles that are pictured in the diagram. I say that they are a linear pair. That's our given. And then at the conclusion, which comes after the word proof, I repeat the names of those two angles, ABC and CBD, and I say that they are supplementary. So when we set up a proof, we always seek for maximum specificity. We always have a diagram with labels so we can name the objects in the diagrams, and then in the given and what we are asked to prove, we refer specifically to that diagram and the names that are present in it. All right, so here's another. Prove that the sum of the angles of a triangle is 180 degrees. Excuse me. Again, we will not prove this yet. Simply set up the proof. Actually, this is not something that will be ready to prove until the chapter on parallels, but we can certainly set the proof up. Okay, oops, I didn't write the conditional, so I'll do that. So if a triangle is given, that could perhaps be put in a different way, but that works. So if a triangle is given, then the sum of its angles is 180 degrees. Okay, so there's the conditional statement, which is important because we need to know what the given is and what the conclusion is. So I drew the triangle for you. That's triangle ABC, and that's simply our given. That's the triangle symbol right there. I don't think I mentioned that before. So the given says that we have triangle ABC. And what we wish to prove is that the sum of the angles will be, which will be the measure of A plus the measure of B plus the measure of C, is 180 degrees. And we have thereby achieved maximum specificity. And notice here something that I don't think I mentioned before in chapter 1, where we talked about angles and their names. In certain circumstances, it's acceptable to name an angle simply by its vertex, and we can do that if we have in the diagram only one angle with that vertex, and that's certainly the case for angles A and B and C. Okay, so there's the setup of the proof. We'll give that in the chapter on parallels. Now, let's give some proofs, okay? We know what a proof is. It's an inference chain that takes us from a given to a conclusion. We know how to set up a proof. That is, we know to draw the picture and to make the given, and the proof refers specifically to that. So let's now give some proofs. And here's the first one that we will prove, and this is an extremely important theorem. We will use it all throughout the year. It is called the linear pairs theorem, or LPT for short. You will find that we abbreviate many of the important theorems in the class, and LPT is the abbreviation here. So we wish to prove that if two angles form a linear pair, then they are supplementary. Okay, and I've done all the work in the setup for you. I think the letters are a bit different than what I showed you a moment ago, but of course the letters are ultimately not important just so long as you're consistent about it. Okay, so here's a diagram where we have a linear pair, ACD and BCD. So I say that in the given that those two angles form a linear pair. And then what we wish to prove, that is the conclusion, is that angles ACD and BCD are supplementary. Now, let's actually give the proof. And this is a moment of great importance for us. This is the first time where we do the sort of work that is most important to this class. This is the first time where we actually become a theorem prover. Okay, so here's the proof. In column form, this is the kind of inference chain that we saw before. I recreated the diagram for us so we can have easy access to that. Notice that line number 1 is the given, that angles ACD and BCD are a linear pair. That's just like the table, the column type proofs that we saw before. And notice that sometimes the given can extend over multiple lines, a 1, a 2, a 3, and so on. Sometimes we compress multiple statements into a single line, call all of that the given. It just depends on the situation. Doesn't particularly matter. All right, so let's go to line number 2. Raise CA and CB form a line. And you know how inference chains work, right? This line number 2 didn't drop out of the heavens with no reason at all. Instead, it follows from some previous line or lines in the proof. And of course, the only line that it could possibly follow from is line number 1. And it follows from line number 1 by the definition of linear pair. That definition says that a linear pair, that the non-common sides of a linear pair form a line. So we just simply apply the definition and we get line number 2. Okay, line number 3, angle ACB is straight. Well, think about the definition of straight angle. It says an angle is straight when its two sides form a line. But that's what we were told on line number 2. So line number 3 follows from line number 2 by, oops, that is very messy, by the definition of linear pair. Excuse me, by the definition of straight angle. Yeah, a straight angle is by definition an angle whose two sides form a line. And then look at line number 4. We now say that that straight angle measures 180 degrees. Well, where were we told that a straight angle measures 180 degrees? Well, we were told that in the straight angle postulate. So it follows from line number 3 by the straight angle postulate that our angle ACB measures 180 degrees. Okay, now we're about to have to use the angle addition postulate. That's how we'll get addition in here, and we need addition because supplementary ultimately says that two angles sum to 180 degrees. Well, the way that we get to the angle addition postulate is that we need to note, first of all, that D lies in the interior of angle ACB. And how do we know this to be true? Well, that follows from the definition of linear pair. Okay, the definition of linear pair guarantees that when we have a linear pair, that common side lies in the interior of the angle formed by the non-common sides. And then once we know that D lies in the interior of ACB, we can apply the angle addition postulate, because that's exactly what the angle addition postulate needs to work. It needs an angle with a point in its interior. So it now follows from 5 by the angle addition postulate, which we abbreviate as AAP, that ACD plus BCD is equal to ACB. Now, look at so here we are at line number 7. Look at 2 previous lines. Look at line number 6 and look at line number 4. Okay, we're told that ACD plus BCD is ACB, and then we're told that ACB is equal to 180 degrees. So of course it follows from those two that ACD plus BCD is 180, and it follows by the transitivity of equality. And let me abbreviate that as TOE, transitivity of equality. We have some fun abbreviations, that's one of them. So this is TOE, and I do hope you see the structure here, right? We have one thing, the sum ACD plus BCD equal to a second thing, ACB, and we have that second thing, ACB, equal to a third thing, 180, so it follows that the first is equal to the third, and that's exactly what we say on line number 7. And then consider line number 8. We now say that the angles are supplementary. Now, how do we know to say that? what has occurred previously in the proof that allows us now to infer that angles ACD and BCD are supplementary? Well, that's simply line number 7. On line number 7, we say that the sum is 180, and so we know by the definition of supplementary that those two angles are supplementary. And with that, the proof is complete. And that's the first proof of the semester. There it is. We have just proven with materials given to us, that is the definitions and postulates presented in chapters 1 and 2, that it must then follow that linear pairs are supplementary. And let me add a little something at the end of the proof. It's a box. And what that box means, it's not really part of the proof and it's not necessary, but what that box says is, hey, the proof is complete. We did what we set out to do. And I'll often use a box at the end of a proof. Okay, so next theorem. Prove that if two angles of equal measure form a linear pair, then each is right. Okay, then each is right. Now, before we launch into this proof, let me make an important point that really gets at the structure of this class, what we do in this class. That theorem that we just proved, the linear pairs theorem, now that it has been proven, can be used in later proofs, okay? If we need to know that a linear pair is supplementary in a later proof, we don't have to go back and reprove it again. Instead, we can simply make reference to the linear pairs theorem and then use that conclusion that it gives us. That is, if we have a linear pair, we know that it is supplementary. So LPT is a reason that it can appear under the by column, and you will see that happen in just a moment. Okay, so let us prove the T theorem. So let's see. Okay, so if we have a linear pair and they are equal in measure, okay, so I just created a linear pair that are equal in measure, we will say that each is right. And I believe in this case, we can make do simply with numbers for the angles, okay? So here's the given. It's actually two-part. Angles 1 and 2 are a linear pair. And here's the second part of the given, that the measure of angle 1 is equal to the measure of angle 2. And what we wish to prove is that angles 1 and 2 are right. All right, so let's put this proof together ourselves. How about just simply S for statements, F from, and B from by. Okay, so we know what line number 1 is. It's simply the given. For the sake of time, allow me not to repeat the given here. We know precisely what it is. We've written it once already, and I hereby give you permission to do the same if the given has already been stated up top. Okay, so, well, we have a linear pair. And the previous theorem, the first theorem that we proved, the linear pairs theorem, tells us something about that. It tells us that angles 1 and 2 are supplementary. Ooh, let me fix that. They're supplementary. We don't have to go and reprove that again. It's already been proven once, so let us simply use that result. Okay, so that follows from the given by the linear pairs theorem. So there it is. A theorem that has previously been proven can be used as a reason under the by column. Okay, so we know what supplementary means, right? It means that the measure of angle 1 plus the measure of angle 2 is equal to 180 degrees. That clearly follows from line number 2 by the definition of supplementary. And then, well, what else do we know? That is, what else is given to us here? Well, we know that the measure of 1, is equal to the measure of 2. So that allows us to do a substitution. So where we see the measure of 2 on line number 3, we can replace that with angle 1. So line number 3 then becomes this. The measure of 1 plus the measure of 1 is 180 degrees. So that follows from, well, we made use of the equality that was in the given to substitute into line number 3 to get measure of 1 plus measure of 1 is 180 degrees. So that's SUBST for substitution. And then, of course, just a little bit of algebraic simplification type work. Measure of 1 plus measure of 1 is twice the measure of 1. So we now have twice the measure of 1 is equal to 180 degrees. That follows from 4 by substitution. Remember that anything that you would be tempted to call just algebraic simplification for us is substitution. And then at this point, we would like to divide both sides by 2. So we have 2 times the measure of 1 divided by 2 is 180 degrees divided by 2. And that follows from line number 5 by the division postulate, which I'll simply call div. And then line number 7, well, look at line number 6. We have 2 over 2 on the left, which becomes simply 1, which means then that we simply have the measure of angle 1. And on the right-hand side, we have 180 degrees over 2, which becomes 90. That's another example of substitution. We've seen that kind of move before in previous proofs that we have done. And then, well, of course, it would follow that that angle 1 is a right angle, but we would also wish to know that angle 2 is a right angle as well. But consider line number 7 together with the given, or that part of the given that says that the measure of 1 is equal to the measure of 2. Well, the measure of 1 is 90, but the measure of 1 is equal to the measure of 2. So then it also follows that the measure of 2 is equal to 90 degrees. And that comes to us by means of the given in line number 7 by, there it is again, tau, the transitivity of equality. And then consider lines 7 and 8. Okay, one of them tells us that angle 1 is 90. The other tells us that angle 2 is 90. So it then follows that, of course, both angle 1 and angle 2 are right. And that follows simply by the definition of right angle. And again, you'll allow me to abbreviate. And with that, the proof is complete. And as I said a moment ago, I will very often put a box at the end of a complete proof that simply says, hey, we did the work that we set out to do. So the proof is complete. All right, the complement theorem. This says that if the non-common sides of 2 adjacent angles are right, then those 2 angles are complementary. I won't take the time to do this with you. I've set the proof up for you on the worksheet. You should be able to carry it out on your own. You will find, however, that the proof is very similar to the proof of the linear pairs theorem, so you should be able to follow that particular proof, what we did there. All right, so same supplements theorem. It says that if 2 angles are supplementary to the same third angle, then those 2 angles are equally. And let us go ahead and get specific. It says, if we wish to name the angles, that if angle A is supplementary to angle C, and angle B is supplementary to angle C, then the measure of A is equal to the measure of B. Again, I'll have you do this yourself on the worksheet. You should be able to do this, actually. It's not particularly difficult. Now, vertical angles theorem. This is the second of our really important theorems that will get used all throughout the class. The first of the really important theorems was the linear pairs theorem. Now we have the vertical angles theorem, which says that if 2 angles are vertical, then they have equal measures. Now, this proof could be made complex. It could be made long. But if we make use of the same supplements theorem, which I mentioned a moment ago, which says again that if each of 2 angles are both supplementary to the same third angle, then they are equal. If we use that, the proof of the vertical angles theorem will be actually quite short. Okay, so proof of the VAT. Well, what do we need to prove the VAT? Well, we got to set the proof up first of all. So let us create a pair of vertical angles, and we know how to create a pair of vertical angles. This goes back to our definition in chapter 1. The way we do it is we intersect a pair of lines, and then we take a pair of angles that lie opposite one another. Okay, so I'm going to call those angles 1 and 2. Okay, so here is our given. Angles 1 and 2 are vertical. And what we wish to prove is that the measure of angle 1 is equal to the measure of angle 2. Okay, that will be our conclusion. Now, let's give the proof. So we have statements that come from something that happened previously in the proof by application of some definition postulate, or we now know previously proven theorem. Line number 1 is always just simply the given, and you'll allow me not to state that given again. Okay, so now, oops, I made a mistake. I got ahead of myself. Allow me to correct what I mean to say. Before we launch into this proof, here's something that I would like us to do. Let us label another angle that's present in the diagram, angle 3. Okay, you can always do this if you like. If some object is present in the diagram that you've created, you can give it a name. You might wonder why we would need to name this angle, but you will see that in a moment. Understand initially that this is perfectly acceptable. Of course, that object is there, so of course we can give it a name. So consider angles 1 and 3. We know the relationship that they have, right? Together, angles 1 and 3 form a line. That is, they're a linear pair. Now also look at angles 2 and 3. Okay, you have to sort of shift your point of view, kind of to rotate it a little bit. Angles 2 and 3 also form a linear pair. This is really the key to the proof. And they form a linear pair because, of course, together they make a line. So angles 1 and 3 are a linear pair. And I tell you what, I'm going to go ahead and write this on the same line. Angles 2 and 3 are a linear pair. And the reason that it's acceptable to do this is that both of these statements follow from the same prior statement by the same rule. They both follow from line number 1, the given, by the definition of linear pair. When you create two vertical angles, of course you create linear pairs. So by definition of linear pair, it follows that 1 and 3 are a linear pair, and that 2 and 3 are a linear pair. Okay, now ask yourself, what do we know about linear pairs? They're supplementary. We proved that, right? That's the linear pairs theorem. So it now follows that angles 1 and 3 are supplementary. And it also follows that angles 2 and 3 are supplementary. And that follows from line number 2 by an application of the linear pairs theorem, which tells us that linear pairs are supplementary. Okay, now consider what we have on line number 3. Here's another way here's a way to rephrase what it says on line number 3. We have two angles, namely angles 1 and 2, each of which is supplementary to the same third angle, that is angle 3. And that's what the same supplements theorem is about. It says that if we have two angles, each supplementary to the same third angle, those angles are equal to one another. Okay, and you will have proven that at this point on the worksheet. So it now follows immediately that the measure of angle 1 is equal to the measure of angle 2. So let me write that down. It follows that the measure of 1 is equal to the measure of 2. That follows from line number 3 by the SST. That is the same supplements theorem. And with that, the proof is complete. So in just a moment, I will write the little box to indicate that the proof is complete. Yes, we set out to do what we intended to do. This is the vertical angles theorem. And this is, I think, really quite an extraordinary little theorem because it's not, I think, obviously true when you first encounter it. That is, it's not obviously true that vertical angles must be equal to one another. And if you are told that it is true, of course, you will wonder why it is true. Well, the proof answers that why question. It tells you why vertical angles must be equal, and the explanation is that they must be equal because they're each supplementary to the same third angle. All right, so perpendicular lines theorem. I won't do this one with you. It's another worksheet proof, but I will talk about it a little bit with you. What it says is this, is that perpendicular lines intersect to form four right angles. Now, perhaps this will seem a little mysterious to you initially, not that it's true, but why you would be asked to prove it, because you perhaps thought that it's just simply part of the definition of perpendicular. But it's not. The definition of perpendicular is this. Two lines are perpendicular when they intersect to form a right angle. Now that A means at least one, okay? So what we really have to prove here is this, is that if two lines intersect in such a way as to produce at least one right angle, then actually they have to have produced four right angles. So there is then work that we have to do here. So here's the diagram. I have two lines that have been marked perpendicular. You can see the right angle symbol there in the diagram. And I have chosen that angle 1 will be the angle that we know is right. And then what we have to prove is that angles 2, 3, and 4 are also right. And as for how you would prove this, well, I'll let you think about the details, but it's not particularly difficult. Ask yourself about the relationship between angles 1 and 2. What are they? They're a linear pair, of course, right? Which means that they sum to 180 degrees. But the measure of angle 1 we know is 90 degrees. So what then does that mean about the measure of angle 2? It would have to be 90 degrees as well. Okay, so we can now conclude that the measure of 2 is also 90 degrees, and then think about the relationship of angles 2 and 3. They're also a linear pair, which means that they're also supplementary. That is, their sum is 180 degrees. But at this point in the proof, we know that the measure of 2 is 90 degrees, so a little bit of algebraic work will get us that angle 3 is 90 degrees. And we can do the same for 4 as well, right? So we can work around in this way, and we can find ourselves with the conclusion that 2, 3, and 4 have to be right angles as well. Okay, so I'll let you write out the details of this, but I think it should be clear what it is you need to do. All right, now that's those first set of theorems that we proved, we at least discussed, some of which we proved, concerned angles and angle relationships. Now we have some theorems that concern segments and segment relationships. The first of these are they concern angle and segment and angle relationships, but we'll just give the the segment varieties of the proofs. And the first of these are the midpoint and angle bisector theorems. The midpoint theorem says that every segment has a midpoint. The angle bisector theorem says that every angle has an angle bisector. This is something that we have talked about before. These are immediate consequences of the ruler and protractor postulates, respectively. And since these proofs can really be done in just one step, we won't take the time to write them out. But do know that this must be true, and so we can use this if we need to at any point along the way. That every segment has a midpoint, that every angle bisector has, that every angle has a bisector. All right, so let's actually write out some proofs now, or at least discuss how they would be written out. The first of these that we'll actually take the time to consider in detail is the halfway theorem. Here's the segment version. It says that if C is the midpoint of segment AB, then AC is equal to BC is equal to half AB. AC and BC are, of course, the subsegments created when that midpoint is dropped in. And what we say about them is that each is half the length of the whole segment. For angles, this says that if we take an angle and add in the angle bisector, the two subangles created is half, each of those is half the measure of the whole angle. We'll prove the segment version. And I think that this one is so simple that no diagram is needed. Okay, so sometimes diagrams are not particularly helpful. Mostly they are, but sometimes they're not. They're not, so I won't actually create it for us. And we also won't take the time to do the angle version because the angle version is exactly similar in form to the segment version. So all the various moves that we have to make in the segment version, we'd also have to make in the angle version. The only difference would be is that we would name angles instead of segments. Okay, so here's the proof set out in table form, usual way with statement by and from. So the given here is that C is the midpoint of segment AB. Okay, so first of all, we know that AC is equal to BC. That follows from 1 by the definition of midpoint. And then we say that AC plus BC is equal to AB. Well, that just simply says that part plus part is equal to whole. And that would be true whether C was a midpoint or not, just so long as C is on AB between A and B, that would follow. So that follows from 1 by the segment addition postulate, which we once again abbreviate as SAP. So segment addition postulate, there, finally. And then consider the interaction of lines. Oops, I got the line numbers wrong, didn't I? So let me go and fix this. So that should be 3 and 4 and 5 and 6 and 7 and 8. Sorry, I'll go and fix that on the PowerPoint, but let's get it right here. So now consider the interaction of lines 2 and 3. 3 says that AC plus BC is equal to AB. But then we're told that AC is equal to BC. So that means that the AC, and actually I'm going to go the other way around. Could have done it that way. But what that tells us is that the BC in AC plus BC is equal to AB can be replaced by AC because BC is equal to AC. So if we bring 2 and 3 together by substitution, they entail that AC plus AC is equal to AB. And then look at line number 4. We have AC plus AC, which simplifies down to double AC. So this follows from line number 4 by substitution. And then we divided both sides by 2. This is the kind of maneuver that you've seen take place a number of times. This is really just algebra. So what we did is we took line number 5 and we divided both sides by 2. And then we simplified what resulted. So on the left side of line number 6, we had 2 over 2, which is 1. So that leaves us just with AC. And then on the right-hand side, well, nothing happens there at all, but we did simplify the left-hand side. So this line number 7 follows from line number 6 by substitution. And then we wanted to conclude that AC is AB over 2, and we also wanted to conclude that BC is AB over 2. That's the total conclusion that we wanted. Well, look, line number 7 says that AC is AB over 2, and then back up on line number 2, we're told that AC is equal to BC. So if AC is AB over 2, so is BC. So this follows from lines 2 and 7 by, you guessed it, that's the transitivity of equality. So there's the box. We will put that in, and the proof is complete. Equal wholes equal halves. And I think that I will just discuss the segment versions of these. There are also angle versions of these, and I think it should be obvious what they are. So the statement of the segment version of this says that if two segments are equal and each is divided in half, then the halves created are equal. That is, halves of equals are themselves equals. I'll let you do this in the problem set, but here is a picture. Okay, so of course we know that we should have a specific diagram with named objects that we can then refer to in our proof. So the given is this, AB is equal to DE. That is, the whole of one segment is equal to the whole of the second segment. We're told that C is the midpoint of the first, that is, C is the midpoint of AB. We're told that F is the midpoint of DE, F is the midpoint of the second segment, and then we wish to prove that those halves are equal. And let's say specifically that we'll prove that AC is equal to DF. So a half of one is equal to a half of the other. And I think you should be able to do this. All right, so the many parts theorem, it says that if a segment or an angle is divided into two or more parts, the whole is the sum of all of those. Well, if we have only two parts, that's simply the segment addition postulate, or if it's an angle, the angle addition postulate. So let us assume that we have more than two. So let us assume in particular that we have 2 points in the interior. And if we were to have more than two, that is, if we were to divide the segment up into more than 3 parts, well, the proof would be very similar. So let us show the proof in this case. So here's the setup. We have segment AB with points C and D in its interior, as shown in the diagram. And we wish to prove that the sum of those 3 parts created, that is AC, CD, and DB, is AB. Now, how are we going to do this? So statement from by. The initial statement is always just simply the given. And then let's simply do some work, okay? So AC plus, I have to be more careful about that. I think I can make that not happen, but I have to remember not to let it happen. So I know that AC plus CB is equal to AB. Now, what is that? That's like we ignored point D, right? And just considered the 2 parts of AB, that is AC and CB. So that follows from line number 1 by the segment addition postulate. And now let's do the same thing to CB. CB has 2 parts, doesn't it? CB has the parts CD and DB. So we could say that CD plus DB is equal to CB. And that is the segment addition postulate applied to, once again, the given. That's just simply another part of the given. And then consider lines 2 and 3 together. Line number 2, AC plus CB is equal to AB. Line number 3, CD plus DB is equal to CB. Oh, so line number 3 tells us what CB is equal to. It's equal to CD plus DB. So by substitution, anywhere else that we see CB, we could replace it with CD plus DB. So that's exactly what we're about to do. So the CB on line number 2 becomes CD plus DB by substitution. And with that, the proof is complete. So how actually do you prove that a segment is the sum of all of its parts? If it has more than 2, if it's just 2, it's just the segment addition postulate. If it's more than 2, well, it's just repeated application of the segment addition postulate together ultimately with substitution. That's how that gets done. All right, so equal parts equal wholes. This is our next theorem. It says that if we could pair off the parts of 2 wholes, it could be a segment or an angle, so that the paired parts are equal, then the wholes are equal too. All right, so here's an example of what I have in mind. So let us say that we have 2 segments, A, B, and CD. and each has been broken up into two parts. The parts of AB are AE and BE. The two parts of CD are CF and FD, and let us say that those parts are equal. That is that AE is equal to CF, that EB is equal to FD, then it will follow that the holes are equal as well. Now, actually, I think for the sake of time that I won't go through and do this, but as you might guess, this ultimately involves the segment addition postulate and substitution. Okay, hole minus part. If we have two holes that are equal, and those can be segments or angles, and we can pair off the parts in such a way that all the part pairs except for one are equal, then the final pair has to be equal as well. That is, if you start with equal holes and subtract off equal parts, the parts that remain have to be equal as well. Now, as for what the segment version looks like, we have that holes are equal. That is, AB is equal to CD. Those are our two hole segments. We have a part of one, AE, equal to a part of the other, CF, and we wish to prove that BE is equal to DF. And I tell you what, I'll do this one with you. So statement and from and by. And let's say that this will be the last proof that we do together. So line number one is the given. Okay. And as for how this is going to be done, well, AB is equal to CD and AE is equal to CF. And we wish to prove that B is equal to DF. That feels like subtraction, right? So how are we going to do subtraction? Well, we have to start with something from which we can subtract. And I think what we ought to start with is this, that the whole AB is equal to the part AE plus the part BE. And likewise, and for the same reason, CD is equal to the part CF plus the part DF. And both of those follow from the given by the segment addition postulate. Now, what are we going to do with this? Well, at some point we're going to have to subtract, but I see another move that we can make almost immediately. Look at what we're told in the given. We're told that AB is equal to CD. But we know that AB is AE plus BE, and we know that CD is CF plus DF. And what do we know about things equal to equal things? They're equal to one another, of course, so it follows that AE plus BE is equal to CF plus DF. And that follows from, well, let's see, what did we apply? We applied the given, and we also applied line number 2, and that's the transitivity of equality, okay? Now, let us think about what we can do with this. We wish to prove that BE is equal to DF, right? So there they are, the equation that we have, that BE is equal to DF. So somehow or another, we have to peel away the A, E, and the CF. Oh, we need to subtract away, right? We need to subtract away AE from one side and CF from the other side, but we can certainly do that because AE and CF are equal to one another. So here's what we can say. We can say that AE minus AE plus BE is equal to CF minus CF plus DF, right? And look at what we did, right? We took line number 3, we subtracted AE from the left, we subtracted CF from the right, but we can certainly do that because those are equal to one another, right? So we applied the given, which told us that AE and CF are equal. We also used line number 3, and the postulate was subtraction, okay? And then let's think about what line number 4 becomes. AE minus AE is, of course, just simply 0. So on the left-hand side, we're left with BE. CF minus CF on the right-hand side is also 0. So we're simply left with DF. So this line number 5 follows from line number 4 by substitution. That's what we call it when we algebraically simplify the way that we did. And with that, the proof is complete. And then the final proof that I will have you do, and I think I'll simply let you do this on the worksheet, it says this: if a segment or an angle is divided into parts, then the measure of whole is the greater than the measure of any part. Okay, and we'll do the segment version again, or I'll have you do the segment version. The angle version is exactly similar. Now, to be able to do this, I have to offer you another definition. And the definition is the definition of greater than. It says that one quantity is greater than another when it is that other plus some positive quantity. So in symbols, it says that if A is equal to B plus P, and P is some positive quantity, then A has to be greater than B. I mean, this makes perfect sense, right? Of course, 5 is greater than 3. And why is 5 greater than 3? Well, 5 is equal to 3 plus 2. That is, 5 is 3 plus some positive quantity. And so for us then, by the definition of greater than, it follows that 5 is greater than 3. And that's what you will use in this case. So we have segment AB with C in its interior. And we wish to prove that AB is greater than AC and AB is greater than BC. And how will this go? Well, segment addition postulate that AB is AC plus CB. And, well, what follows from that? That AB is AC plus some positive quantity, CB in particular, but it doesn't particularly matter for us now. And since AB is AC plus some positive quantity, it will follow by the definition of greater than that AB is greater than AC. And for the same reason, it will follow that AB is greater than BC, because AB is BC plus the positive quantity AC. So this actually should be a really, really short proof, like 3 or 4 lines tops. All right, with that, we are done. So you have seen like the basic sort of ingredients of this class. You have definitions of geometrical objects, the important ones for the class. You know how to name them, you know how to draw them, you know what an inference is, you've seen an example of inference chains, and now we have called certain inference chains proofs, and you've proven some really important theorems. And let me just remark again that the ones that will get used most often in later work that we do are the linear pairs theorem and the vertical angles theorem. All right, so next time we'll talk about one of the most important topics of the chapter. We will talk about triangle congruence.